Hello and welcome. This is the summary to the first half of Chapter 10. Gases have many characteristics I'm sure you're familiar with. Gases generally behave similarly. They're composed mainly of non-metallic elements with simple formulas, relatively low molar masses. Unlike liquids and solids, gases expand to fill their containers, are highly compressible, and generally have low densities. Two or more gases can form a homogeneous mixture. So gases tend to behave as non-interacting particles. We'll see that's the primary basis of what we call the ideal gas behavior, fitting gases that are described by the ideal gas law. You probably remember dealing with this equation perhaps in high school chemistry or maybe even physics. To get a sense of some of the range of some molecular compounds that are gases at room temperature, hydrogen cyanide, very toxic, smells like bitter almonds. H2S smells like rotten eggs, also very toxic. Carbon monoxide, toxic but colorless and odorless. If you have a gas furnace, I highly recommend, or any kind of gas equipment in your house, I would highly recommend a carbon monoxide detector, especially in the winter. If you do have a natural gas type furnace, you should change your furnace filter at the start of winter so you don't choke out the oxygen, so when you combust your hydrocarbon that you can actually make CO2 and not carbon monoxide. So maybe check your furnace filters to prevent carbon monoxide from forming. But CO2, of course, is a gas at room temperature, as is methane, ethylene, propane, nitrous oxide, nitrogen dioxide, ammonia, sulfur dioxide. Some of the key characteristics of many of these molecules, though not all of them, but many of these molecules are nonpolar, and a few of the ones that are polar aren't particularly polar. So we don't see things on this list that tend to have oxygens with hydrogens attached. So we'll start to see in the next chapter that some molecules have stronger attractions and hence would be liquids at room temperature. So these generally, though not always, are the nonpolar set of molecules or the molecules that aren't highly polar. Some of the properties that define the state of a gas would be the temperature, the pressure, and the volume and the quantity. And you probably remember this equation, PV is equal to nRT. So let's not pretend like we don't know this equation, but this relates the pressure of a gas, to the volume of a gas, to the quantity as the number of moles, and to the temperature. And so let's connect our quantities here. Let's actually connect our pressure, the volume, the amount of substance as the moles, and then T for temperature. R is a constant here. This is the ideal gas constant. We'll talk more about that later. So pressure is the amount of force that's applied onto an area. So it's a force exerted onto a square area. We can think of the pressure that's being exerted onto the surface of Earth due to the gravitational force pressing the atmosphere towards the surface of the Earth, and then the actual mass of the surface area, or the mass of the atmosphere. So force is equal to mass times acceleration. So if we're thinking atmospheric pressure here, we'd be thinking of the mass of the atmosphere times gravity being exerted on the surface area of Earth. And it turns out that it's about 10 to the 4 kilograms that would be sitting atop of a square meter. So if you had 1 square meter surface area on Earth, and think about the vertical column extending upward from this on this cross section, that is about 10 to the 4 kilograms. Gravity is about 9.8 meters per second squared. So this pressure that's being exerted due to this mass is about 10 to the 5th kilograms meters per second squared. And then that was divided by the meters squared from the surface area. So the unit here would be 10 to the 5 kilograms meters to the minus 1 seconds to the minus 2. This is our SI unit of pressure that we call the Pascal. So atmospheric pressure is approximately 10 to the 5 Pascal. So atmospheric pressure is the weight of air per unit of area. So it's the amount of weight that's sitting per unit area on the surface of Earth. So 1 Pascal could also be expressed as 1 Newton, where Newton is a unit of force. A force coming from a mass times an acceleration. So again, a kilogram meters per second squared would be the unit of the Newton. Divide by meters squared gives us the SI unit of pressure of 1 Pascal being equal to 1 kilogram meter to the minus 1 second to the minus 2. And so a bar, 1 bar, is defined precisely as 100,000 Pascal, or 10 to the 5 Pascal, or 100 kilopascal. Now, this is not the most common unit. In fact, I don't think I've ever once used that unit in an example in this class, though I think weather meteorologists tend to use it as their base unit for like the millibars of pressure of, say, a storm system. More common units in chemistry would be millimeters of mercury or torr. Interestingly, these units are synonymous with each other. We'll see it down here. 1 atmosphere is equal to 760 torr, 760 millimeters of mercury, 101.325 kilopascal, or 1.01325. That should be 1.01325. But again, we don't do conversions with the bar. These are all exact conversions. I kind of don't like that the slides, whoever made these slides, with those decimal points in there, because I don't think you need them. It's exactly 760 torr in an ATM. As written, might make you think that there's only 3 significant figures of torr in 1 atmosphere. These are all exact conversions. Okay, so what we have shown here is a barometer. So the way a barometer would work is it's a device used to measure atmospheric pressure. We would take a tube, evacuate the air from the tube, dunk it quickly into a dish of mercury, and then the mercury is going to be pulled up into the tube by the vacuum until at which point the height here is equal to atmospheric pressure. And if you think of using mercury, that's where the millimeters of mercury come in, that this should equal, in terms of a height, whatever the height of mercury is to equal atmospheric pressure. So let's say that we make this column on a day where atmospheric pressure is 0.975 atm. Then in millimeters of mercury, that should be times 760 millimeters of mercury. That's 741. So we should have about 741 millimeters of height for where that mercury is being pulled up to. So then if we have a day where more pressure, if the atmospheric pressure is higher, then we're pushing down, the atmosphere is pushing harder down in the mercury dish, so we're going to see the height in the column go upward, indicative of a higher atmospheric pressure on that day. So you can see the fluctuations in the height in the column to fluctuate with atmospheric pressure. Okay, and so then 1 torr is equal to 1 millimeter of mercury, so those units are synonymous with each other. 1 atm, 760 torr, 760 millimeters of mercury. And I'm going to go ahead and just do a line through that unit there. But again, it's the key units that we use in this class: atm, torr, millimeters of mercury, and pascals. One other unit not shown here would be psi, so about 14.70 pounds are exerted per square inch. This is the psi unit. This is maybe a bit more used in the medical field, or just like, say, if you're filling your car tire. Manometer is a device used to measure the pressure of a gas in a vessel. So imagine we have a container. Normally what you would start with is a container that has a valve, and then you would start with this here at atmospheric pressure and the height of your column of your mercury equal. And so then you would open the valve and then see if the gas was higher than atmospheric pressure, at which point it's going to push this mercury down and the other end of the mercury goes upward. And then you can take the height differential, the differential between the height here of the 2 mercury ends, and see that the pressure of your gas is going to be the atmospheric pressure plus that height differential. Well, it's actually shown here. And so the pressure of your gas would be atmospheric pressure plus the difference of height. And then likewise, if your gas is lower than atmospheric pressure, if the pressure of the gas is below atmospheric pressure, then you would see this end going the opposite direction and this end going the opposite direction. And then you just take the difference by subtracting the pressure of the height from atmospheric pressure. So standard pressure, standard atmospheric pressure, 1 atmosphere, 760 torr, 760 millimeters of mercury, 101.325 Pascal, 14.70 psi, or pounds per square inch. So let's look at a couple of relationships between pressure and volume. We can look at the graphs, but let's just think about this. We have a gas sample with a particular pressure, and I maybe can push down on here to change the volume. And so then if I start changing the volume and reduce the volume, make the volume smaller, what happens to the pressure? Pressure should go up. So if we're compressing here, the pressure is going up, the volume is going down. So it means the pressure and the volume are inversely proportional to each other. So if we make the volume smaller, we're making the pressure higher. So that means that P1 V1 would be equal to a constant. So if we have some initial pressure and volume and some final pressure and volume, you can write this expression. And then we can use this to solve problems whenever the quantity of gas is constant, whenever the temperature is constant. So if you have a closed container at constant temperature, then this equation should hold up. So then we can look at the relationship of volume. So we have a gas at some pressure, and then we are dropping the volume. We are increasing the pressure. So as we go this way, we're increasing the pressure due to the drop in volume. And so then if you do a plot of the volume versus 1 over the pressure, then that plots as a straight line. Charles' law explains the connection between the volume of a gas and its temperature. So you have a balloon, you heat it up, it expands. You have a balloon, you cool it down, it contracts. No big surprise here that volume and temperature are directly related. So if you increase the temperature of a gas, you increase the volume, and then likewise, if you decrease the temperature, you decrease the volume. So your V1 over T1 would be equal to a constant, and then hence V1 over T1 would be equal to V2 over T2, provided that we have a constant number of moles for our gas and a constant pressure. So a constant pressure, the balloon expands, maintaining a constant pressure inside the balloon. So if we say had 1.25 atm in the balloon here, we'd have 1.25 atm in the balloon here. We just have a larger volume due to the change in temperature. We could also do a mathematical relationship here of plotting the temperature versus the volume. The only thing being you want to think about the temperature in well, you may want to think about it in Kelvin, though this plot here is actually showing the temperature plotted in degrees C, that as you take a gas, warm it up, volume increases, gas, cool it down, volume decreases. Avogadro's law looks at the quantity connection to the gas, and perhaps more interestingly finds that if you take a gas at atmospheric pressure, at standard atmospheric pressure, so 1 atm, of a gas at 0 degrees C, and you put a mole of gas, so a mole of helium is 4 grams, a mole of nitrogen is 28 grams, a mole of methane 16 grams. So these all correspond to 1 mole of those gases. The number of gas particles, Avogadro's number, so we have a mole of gas in the container, so we have an Avogadro's number of gas molecules, that all of these gases occupy the same volume. So the volume of the gas is exactly the same for all of these quantities. And so, of course, if we wanted to put more quantity of gas inside the container, and we wanted to maintain a constant pressure, then we'd have to expand the container. So our connection between N and V, so the quantity of gas is directly proportional to the volume. So if I put more moles in the container, we have to expand the volume if we want to keep pressure and temperature constant. So we can write N1 over V1 equals N2 over V2, as long as we have a constant pressure and temperature. Okay, so of course we could put all these quantities together. So if we go back and recognize that volume inversely proportional to pressure, so that's Boyle's law, volume directly proportional to temperature, that's Charles' law, volume directly proportional to the number of moles, Avogadro's law, then we get that the volume is directly proportional to NT and then inversely to P. And so that means that the PV divided by NT would be equal to a constant. And we take that constant to be the ideal gas constant R. And so gases that obey this equation are said to be ideal gases. And so then gases that obey this equation are gases where the moles aren't sticking together, where the particles don't interact with each other. So we need N and the particles of the gas to be non-interacting particles. And another maybe smaller correction or consideration is that the gas pressure should be relatively low enough such that the particles of the gas don't occupy a large portion of the container. So you might say that the volume of the gas is negligible, meaning that there's enough space for the gas to distribute that they're not using an appreciable portion of the volume of the container. And so we'll see later towards the end of this chapter that, of course, we can violate or we can have issues with both of these scenarios where at relatively low temperatures, so at low temperatures, we can have cases where particles will begin to interact because they're going to start to form droplets. Droplets will be the particles interacting and having intermolecular forces together. And then we'll also see at high pressure, then the volume of the gas really becomes a non-negligible quantity, and so the gas will be occupying a non-negligible portion of the container when we start pressurizing the gas. So at high pressures, the gas starts to occupy a non-negligible portion of the container. So let's take a closer look at R. So we could take R, we could solve for these. This might be kind of interesting. So let's set R equal to the ideal gas constant equal to PV over NT. We can actually play around a little bit with the Avogadro's finding that 1.00 atm was the pressure of a gas that had 22.4, it's actually 0.415 liters if you write it more precisely, for the volume of a gas, for 1 mole of the gas at STP, and that's 273.15 Kelvin. Okay, so let's define something real quick in this chapter, that STP, standard temperature and pressure, would be 1 atm, 273.15 Kelvin. Why that specific temperature is because that's 0 degrees C. So you might think STP, standard temperature and pressure, would be 298 Kelvin, and it's actually 0 degrees C, not 25 degrees C. So anyways, if we plug these numbers into a calculator, it's good. 22.415 divide by 273.15. We should get the ideal gas constant. So I get 0.08206. And so then the units, liter atmospheres per mole Kelvin. So this would be liter ATM mole Kelvin. So I tend to write that, how it's written on the left. And so that's the liter atmosphere per mole Kelvin. And so we could obviously convert our units here a few different ways. Like, for example, we could just say, okay, what if this is 760 torr instead of ATM? Then we get the torr liter per mole Kelvin. So if we just do that times 760, we get 62.36. We get this number here for the torr times the liters per mole Kelvin. But there's a different set of units here and here that have one number that's the same. Now if you inspect the units, those are actually the SI units. Now how do we get those units there? Well, we might recognize that the atmospheric pressure in Pascal would be 101,325 Pascal times the same volume. The gas still occupies 22.415 liters. We've just changed the pressure to be atmospheres to just atmospheric pressure, but in Pascal, and then divide by the same 1.00 moles, and still at 273.15 Kelvin. And so let me carry that math out. That works out to be let's see. Oh, so that's 8,314 And so that would be Pascal liters per mole Kelvin. Now, if you notice, actually, those are not any of the units here exactly. And so if we convert the liters into cubic meters, so 1 liter is equal to 0.001 cubic meters, then we can get this value in the Pascal per cubic meter. And so if I multiply that by 0.01 to convert liters to cubic meters, then I get 8.314 Pascal cubic meters per mole Kelvin. Okay, so if I have 8.314 Pascal times cubic meters instead of liters per mole Kelvin. Let's go back to what a Pascal is. Remember how 1 Pascal, we wrote this before, is a kilogram, meter minus 1, second to the minus 2, so that's the Pascal. A Pascal times a cubic meter would be kilogram meter squared per second squared. So cubic meter times a Pascal is equal to a kilogram meter squared per second squared. That's a joule. So all of this here is equal to 1 joule. So that's why you see joules per mole Kelvin, Pascal cubic meter per mole Kelvin with the same number, because they are the same, they have the same value, because a joule is simply equal to a Pascal times a cubic meter. Now, most of this, for this stage, and really for about the first half of chapter 5, you see these different units, and really you don't ever use them. I mean, primarily we use this problem here for roughly the first 7 sections in this book. This is just about the only unit of R that we'll use in problems, and we'll find ways to use this and maybe convert pressures if we need to, convert volumes if we need to. And then we'll see for a few problems later in the chapter that we really need to use this value here once we need to throw quantities into SI units. So often I call these two here the SI values of R. So whenever we're looking to calculate quantities and specific SI values, then we're probably using the 8.314 joules per mole Kelvin value. Whenever we're looking to calculate non-SI quantities, like an atmosphere is not the SI unit of pressure, Pascal is. So whenever we're dealing with non-SI units, then usually we're using the 0.08206 number, liter atmospheres per mole Kelvin. So density of gases, we can relate densities of gas to their pressures. Like we can start PV is equal to nRT. Perhaps we can divide both sides by V and by RT. So that would give us P over RT is equal to N over V. So just doing a rearrangement. Moles is times molar mass is equal to mass. Another way of thinking that would be if I take a mass divided by a molar mass, I get moles. So I might be able to rewrite here and say that P over RT would be equal to M divided by molar mass divided by V. And so then if we multiply both sides by M or MM, whichever way we want to write molar mass, let's call that MM. So multiply both sides by the molar mass, then we get pressure times the molar mass divided by RT would be equal to M over V, the mass divided by volume. The mass divided by volume is the density. So density of a gas would be equal to the pressure of the gas times the molar mass divided by RT. So if we have a gas at the same pressure and temperature, the higher the molar mass and the greater the density. So if we recap, if we want to find the density, so if we're trying to calculate the density of a gas, all we need to know about the gas is what it is, so we can calculate the molar mass, the pressure of the gas, and its temperature. So we don't need to know anything about the container that's holding the gas. And also, so our density would again be the pressure times the molar mass divided by RT. I'll probably get a lot of questions about equations. I would probably make sure to know how to get to and from these equations. Like the derivation of this equation is very simple because you just start with PV is equal to nRT, and you just sub mass over molar mass times RT equal to PV, and you just go rearranging for M over V for density. Very easy to get these equations. You don't have to memorize them. If you're memorizing them, I would try to understand where we get them from so that you can derive them or use them as needed. So if we want to relate the, if we want to find the molar mass, so let's say we're trying to find the molar mass, then we can relate that back to the density is M over V is equal to P molar mass times RT. And so then we could set the molar mass equal to MRT, the mass of a gas times the ideal gas constant times temperature, divided by PV. So just doing some algebraic rearrangement solves for this equation here. So Dalton's law of partial pressures deals with gases that don't interact when they're combined in a container. And so then in the container, they act as if they're alone in the container. So our total pressure would just be the pressure that one of the gases would have if it were the only gas in the container, plus the pressure of the other component as if it were the only gas in the container. Likewise, if you have three components, then it would just be as if you add all three of those partial pressures together. So it's like saying if you know you have 1.2 atm of O2 in a container, you have 0.4 atm of, say, N2, and say 0.2 atm of helium, then you can add all of these gases up in terms of the total pressure of the container being just simply 1.8 atm from all of those added together. And so then we can take a ratio of the partial pressure of one component compared to the total. So the pressure of one, so PV is equal to nRT, so the component 1 would be the moles of gas 1 times RT divided by V, and then divide by the total moles, divide by RT, the total moles times RT divided by V. And now RT and V are the same because these gases are in the same container, they're at the same temperature, subject to the same ideal gas law. So the ratio of the pressures of the gas works out just to be the ratio of the moles of the gas. X1 would be the mole fraction. So X is a symbol for mole fraction. It's shown down here. So the moles a component of 1 divided by the total moles defines the mole fraction. So the mole fraction of 1 would be equal to P1 over PT. So the mole fraction of the component 1 would be also not just equal to the moles of 1 divided by the total moles, but also the partial pressure of gas 1 compared to the total pressure. So if we summarize from the last slide, we had that the mole fraction would be equal to P1 over PT. Then you can also write that the partial pressure of component 1 would be equal to the mole fraction times the total pressure. So the mole fraction, the moles of component 1 times divided by the total moles times the total pressure would be equal to the partial pressure of component 1. Okay, so this concludes our introduction to the first half of chapter 10. Thanks for your attention. Hopefully I'll see you guys in class this week.